Good afternoon, everybody. Thank you for sticking to the last presentation. My name is Liping Wang. I'm an associate professor at the University of Wyoming. I also would like to acknowledge my co-author here, Professor Les Nauford from MIT, as well as Professor Amir Badi from University of Guelph. And my student Lichen is working on this project as well. This afternoon, the presentation focused on the interactive indoor and outdoor building energy modeling to enhance the prediction of microclimate prediction as well condition as well as the building energy consumption or building energy demand. So a little bit background and motivation on this. We know we use the urban physics model, such as the vertical city weather generator or urban weather generator. They can basically help us to predict the local or microclimate conditions based on the weather station data at the rural area. With the consideration of urban features as well as the urban heat island effect. However, there's some limitation on those urban physics model. They basically use this single zone um, building energy model regardless of the complexity of the building itself. So the idea here is to integrate our coupling between the two, the urban physics model as well as the building energy model. Particularly in this case, we use Energy Plus, which is prestigious building energy simulation software sponsored by Department of Energy. So we do the iteration, the coupling between each within each time step between the two software, the vertical city weather generator VCWG and Energy Plus to improve the accuracy of the microclimate condition prediction as well as the building energy demand prediction. So specifically, the building physics model going to predict the local climate condition as well as fit the convective heat transfer coefficient to Energy Plus model. And coming back, Energy Plus calculate the anthropogenic heat, the waste heat generation, as well as the surface temperature, and feed back to the urban physics model. So this is a two-way coupling approach, and we also have a more complex one. That's for the we call it a two-way coupling profile. And for that particular case, we'll be able to fit an array of data, and that corresponding to the data set exchange at various building elevations at various floors. So instead of fit one data set, and we fit an array of data sets at different floor level of the building. So that's a more complex data exchange schema. And in particular, the implementation of this coupling is through the, it's called the Semaphore project, Semaphore objects in the Python threading library to synchronize the tasks between the VCWG as well as the Energy Plus. So first of all, the VCWG going to calculate the urban canyon condition, the microclimate condition, and then pass that to Energy Plus. And then Energy Plus going to calculate the waste heat generated and surface temperature and feed back to VCWG and for the next time step. And in particular, after the implementation, we use two existing field measurement data. One is the capital, urban canopy, and aerosol measurement, which is conducted in Toulouse, France in 2004. So it's a 5 minutes data. We compare that in terms of the dry air temperature, outdoor air temperature, and particularly look into the coefficient of variation for the mean square error, as well as the mean Bayes error. And it's a proof of validation of the correctness of our implementation for the two-way coupling approach. So we saw the two-way coupling methods and just using the VCWG and very close in terms of statistical comparison. And similarly, we did another comparison using the bubble, in which is conducted in 2002 in Basel, Switzerland, for urban boundary layer experiment. So that comparison was conducted again for the dry outdoor air temperature at different elevations. Again, we compared the coupling approach between VCWG and the Energy Plus, as well as just the VCWG alone. That's the urban physics model. Again, they are very comparable. So once we did that, we have some confidence about the two-way coupling approach and understand the implementation was valid. So we went on to do some sensitivity analysis and for the urban geometric as well as the surface features. So particularly we look at three different parameters that including the roof to canyon width ratio that directly represent the density of the canyon, the buildings in the urban area. And then the canyon orientation, whether it's north-facing or 45-degree angle, as well as the vegetation fraction, how does those actually impact the energy use profile, as well as the microclimate condition prediction. So this is just a quick overview about those three urban features that we look into. So we found the roof to canyon width ratio has a substantial impact. The cooling energy use can increase up to 15% with the increase of roof to canyon width ratio from 0 to 3 for the medium-sized office building. This model is a prototype model developed by Department of Energy in US. So we run this in Chicago climate for January. So here is showing the result. Another important thing that we look into is to see how does the building energy model complexity as well as the coupling approaches impact both the microclimate condition as well as the building energy consumption or building energy demand. So we look at particularly two case study building. One is again this medium office building model, and the other one is this tall building, which is a high-rise office building. It's a 20-story high. We built them from scratch. And so those are our detailed model. And in the same time, we also look into the simplified model. So particularly for the medium-sized office building, we simplify that to a single zone building energy model. That's just represent the current status of urban physics model. And mainly we have a single zone model involved in them. So that's a simplified energy model. And the other one is a high-rise office building model. That one was we simplify that from 20-story building to use 3 floors to represent them. So that including the first floor and then typical floor and with a multiplier of 18 and then the roof floor. So besides looking to the simplified model, but also we look into the different coupling approach. So there's a one-way coupling approach. One-way coupling basically just running VCWG or UWG for the entire time period and feed the weather data to energy class versus two-way coupling, and we'll be able to pass the data, do the data exchange within each time step. And then there's a two-way coupling profile case, which is more complex. That means we're not only just pushing the data to represent the building with one single data set, but instead at different floor level, we have different data set, and so the local climate condition for each floor could be different. So it's more complex that way. So specifically for the medium-sized office building, we found the deviation between the detailed model and the single zone model pretty significant in terms of the cooling energy consumption and the cooling energy demand. So about 18% to 20, and 18% and 27% respectively. So this is mainly due to the simplification of the building energy model itself from multi-zone model for medium-sized office buildings, 3-story in this case, simplify that to the single-zone model. And for the high-rise office building, you can see that result from the table here. Actually, the simplification is not too bad. It's fairly close to the simplified model result. Is very close to the detailed modeling result. With that's just showing this simplification is very reasonable. This is the figure showing the comparison among different coupling results. So in this case, we're looking at the high-rise office building. That's our 20-story building. And again, we have simplified and detailed model for cooling consumption as well as the cooling demand. So what's showing here on the orange bar is the VCWG and EP profile. That's the one more complex one. So at different level, you're fitting different data for the to VCWG as well as for Energy Plus, and then versus the two-way coupling, just the VCWG underscore EP that represents the general two-way coupling approach. Basically, all the entire basic heat generated from the building just pass to VCWG as a whole from Energy Plus. So that is showing with this blue bar here. The results actually represent to us is especially for tall buildings, adopting a more complex two-way coupling approach with environmental data exchange at various elevation, at various floor height might be necessary in order to improve its accuracy in terms of predicting the energy cooling profile. So this is my last slide, and just to summarize the impact of our study. Basically, we look into the impact of both building energy model complexity as well as the coupling approach on the canyon, urban canyon, microclimate temperature prediction, as well as the building energy profile, energy consumption, energy demand prediction. The light green color here is showing there's a minimum impact with the coupling approach, as well as how does that complexity of the model impact the prediction. The salmon color represents a significant impact. So the conclusion is really, what we saw here is the level of Energy Plus model complexity has limited impact on urban canyon temperature. However, we did observe that the maximum canyon temperature as well as the cooling energy consumption and cooling demand can be substantially different when we use the one-way coupling approach versus this profile-based and detailed two-way coupling approach. And adopting this two-way coupling approach at very detailed level at at various elevations would be important for the tall building urban scale modeling. And potentially we can extend this two-way coupling methods into the large-scale urban building energy modeling. All right, with that, I conclude my presentation. Thank you very much.